Alright, so in this video I want to quickly go over a small script in Grasshopper that lets us create this beautiful diagram of the Mandelbrot set. Now before we get into that, uh, the aim of this tutorial video I wouldn't necessarily call it a tutorial, but I've already basically made the script. I'm just going to go over it and explain why I've used a particular component at each step, and before we get into that, I will discuss what the Mandelbrot set is and its significance in mathematics and all that. So also, if you are new to Grasshopper, I would recommend gaining a little more experience with Grasshopper before you watch this tutorial, otherwise I might just confuse you a lot. So this is definitely not for Grasshopper beginners, because we will be going into loops and all sorts of stuff. So to start off, let's quickly go over what a Mandelbrot set is to understand what our aim is, basically. So the Mandelbrot set is the set of complex numbers C for which the function f of z is equal to z squared plus c does not diverge when iterated from c equals 0. So this basically means that so complex numbers are of course two-dimensional numbers, where the x-axis you can imagine is the our real component of the imaginary number of the complex number, and the imaginary axis is along the y-axis, right? So 0 is of course at 0, but all our real integers and real numbers will lie on the x-axis, whereas any imaginary component, any number with an imaginary component will lie somewhere on this two-dimensional plane above or below the x-axis, right? So uh, the Mandelbrot set is the set of all of those complex numbers which when put in here for in the place of c do not do not cause this function to uh, be unbounded, basically. uh, does not cause f of z to tend to infinity after a number of iterations. So to give a very quick example, we start with z equals 0. So we plug in 0 here, and so 0 is equal to 0 squared plus c. If we take say c equals 1, 1 is also a complex number, just that the imaginary component is 0. So 0 equals 0 plus 1, which is 1. Now we will take that 1 and plug it back in here, which is why it's an iterative process. So f of 1 equals 1 square plus 1, which is 2, and so on and so forth. Now you will notice that that does not remain bounded, so 1 is not part of our set, right? Whereas 0, if we take c equals 0, then f of z equals 0 plus 0, f of which is 0, then f of z is 0 plus 0, and so on and so forth. So it is bounded, right? It does not tend to infinity, or does not keep incrementing or increasing or decreasing infinitely, right? Indefinitely. So that set of numbers, that set of complex numbers that for which this function remains bounded, when plotted, form this beautiful graph, right, which is called the Mandelbrot set. Now, there is also something known as the Julia fractal, the Julia diagrams, which are basically a subset of the Mandelbrot set, but we will not get into that as of now. This is the first published picture. This is basically what we want to arrive at, right? The basic definition of the Mandelbrot set, and we will take this function and try and make a script out of it. Right, so Now that we understand what we need to do, let's just get into it. I am not going to make this script from scratch in front of you because I make scripts very slowly, and I would rather go over a script that I've already made. And I'm sure you'll understand that better. And I don't want to, at this point especially, create confusion for you. So I'm just going to quickly go over this script so that you're able to understand how we got to the point where all of these points form this beautiful diagram. Right. So let's go ahead and hide that and turn this one on. Right, so since this is entirely a mathematically defined diagram, we're going to start off with, of course, numbers. Right? No geometry is involved initially. So what I'm going to say is that I want to essentially create my Cartesian plane, which is just a set of points. So I've basically created a rectangle, which is in Rhino's current units, which is millimeters, is just a 4x4 rectangle, and using a lunchbox component. Actually, this is probably, yeah, it is lunchbox. So using a lunchbox component, I've just created a grid of points in this rectangle, right? And so with that, we have basically some 63,001 points, which is 250 by 250 points. Right? 250 by 250 divisions, and so that is why there's that one extra point. But yeah, so once we have those points, now we can filter through these points to get our Mandelbrot set within this. Of course, we can always increase this number to sort of increase the resolution, but that will of course take time to compute, and we'll see why as we go forward. Right? So I want to take each and every one of these points and deconstruct them. So I will have a series of numbers that correspond to basically each of these points' coordinates. Right? So all of these will be, of course, x and y. We don't really care about the z component because everything in z is 0. Right? So once we have that, we can now come in and talk in terms of complex numbers, where like we had discussed, our x component is the real component and our y component is the imaginary component of the complex number. Right, so with that we now have a complex number at each of these points. Right, so once we have those, now comes in the part where we need a loop. Now for loops, in this case I am using Anemone, which is a plugin for Grasshopper that lets you create quite simple loops. But if you're not new to Grasshopper, then I would highly recommend what I usually stick to, which is scripting it in using a C# or a VB or a Python component. Mostly because it's not, I mean, Grasshopper isn't designed to work with loops very well when scripting visually. So just for that reason, I would not recommend this, but we're going to go this way just in case there are viewers who do not know how to program at all. So for Anemone, we need to give a number of iterations, which in this case we've taken as 10. Right, so that essentially means that this loop will be executed 10 times, and the data will initially be a complex number that is 0, 0, which means 0 plus 0i, the origin, right? And as the loop sort of runs, it will compute the square of the complex number and add it to uh, all of these complex numbers that we have here, and then plug that back in and sort of create that loop. Right, so what this is going to give us is either numbers that tend to infinity, or numbers that do not tend to infinity, or are bounded. Right, so let's just quickly have a look at the output that we're getting here after 10 iterations. Now keep in mind that this is not the first iteration, which is why a lot of them will just basically say NaN, which means not a number. But initially, when the first few iterations will have a lot of more bounded numbers and less numbers that tend to infinity, and we'll see that if we so what I'll do is I'll just quickly trigger this loop so that you can see how this sort of looks as it iterates. So this is the first iteration, and it moves on to the second, third, fourth, fifth, sixth, seventh, eighth, and 10th iteration. Right. So you notice that how the filter sort of slowly tends to the Mandelbrot set. That is happening because of the fact that these numbers are slowly adding to each other and that is defining whether it tends to infinity or is unbounded or bounded. Right. So given that we still do need to check whether the number is bounded or not manually, because this of course is not so the Mandelbrot set can have a lot of branches, right? The number of branches is there is a video that you should probably watch by Numberphile that explains how many branches there are in each of these sort of parts of the Mandelbrot set. And as you increase your iterations, you will be able to see those branches more and more. Of course, our resolution isn't enough to actually see that, but yeah, in the actual diagram, that is how it would look. And for those branches to be visible, you need to basically give it a sort of maximum bound. So in our case, we're going to use 2 as that bound, and we're going to call it an escape value, which basically means that if any of the modulus of any of these points exceeds 2, then that number does not belong to our set. So we're just going to calculate all of the modulus of these complex numbers after this loop runs, and if there are nulls, which will be there because some of these numbers are now NaN and infinity, so those will be replaced. I mean, those will give out a modulus of null. So we want to replace those items with 3, which is more than 2. Right? So we've replaced, this is basically, now we have a list of all of the modulus of each and every point, which is either infinity or 3 or something less than 2. Right, so it is those numbers which are less than 2 that we want, right? All these numbers. These are the numbers that we are interested in, and so we're just going to do a quick check whether each of these numbers is larger than 2 or not, and if it is larger than if it is not larger than 2, which is basically false, then list B will essentially give us our Mandelbrot set. Right, so the script is really simple, uh, and it only basically executes that small mathematical. Essentially, this is all the calculation that's being done. Right, this is it. Everything else is just either setting it up, this portion, or this portion, which is actually comparing the values and getting the points from those values. Right? So this is the main. These are like this is the brains of this entire script. This is what actually calculates the Mandelbrot set. So I mean, it's really simple, right? It's just going to square each of these values and add it to them, right? And that's it. That is what gives us the entire Mandelbrot set. So now, once you have this, you might be wondering, I mean, what do I do with this, right? You could create a mesh with it, right? So we have a Delaunay mesh component, and so we can basically, since we have two sets of points, one which are not included in one set of points which are not included in the Mandelbrot set, and one which are, we can create a mesh made up of these points. Right, of course it doesn't look like anything brilliant just yet, but we could then deconstruct this mesh and maybe apply a little color to it by so let's say we want each point to be colored on the basis of its modulus, or yeah, its modulus. So let's just remap these numbers. Oops. And take the source as these bounds. Actually, we should probably take the ones which have been replaced. And remap these to 255. So, 255. Right. So now we will have values that range between 0 and 255. Actually, we should probably do the opposite, because the ones which are on the outside should be colored and on the inside should not. So let's quickly create let's say our Mandelbrot set should be red in color. So we have a deconstructed mesh here, and we can construct it like this. Okay, we also, so these will only be the values for, okay, no, that's fine. Right. No, so this is why I did not want to start off scripting right here. So I think the issue here is maybe this one. What could be the issue? Let's try mapping this to 0 to 1. which I think it is by default, and use HSL. So this will give us our hue. Still nothing. Why? No. Still nothing. That is probably because just a sec. Yeah, sorry about that. Okay, so yeah, we're recording. So the reason why that was happening was because I was not thinking about it anyway. So we have these two, right? And we've created our mesh and deconstructed it. Now for the colors, we basically want all of the points that are outside our Mandelbrot set to be black, right? And the ones which are inside, we want the color of that to depend on the modulus. So we once again need to dispatch our modulus of each and every value, so that we actually can replace these with just black and not, you know, some weird undefined values. It shows all of these as 3 here, but if you actually look at these values, it's full of nonsense, and infinity and all sorts of weird numbers. So we don't want those numbers, and we just want to replace each of these with black. Right? So we're gonna make a list of just black, which is the same length as the number of points that are here. And for the remaining, we of course have pretty good values, which are from 0 to 2, and we'll just take those values. Like you can see here, the source is, the bounds are 0 to 2, and remap them to 1. You could actually just divide by 2 right here, but still, we'll take that as our hue and merge these two to get this. Right. Now if you want to see what it looks like, so that is iteration 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Yeah. So the reason why it took a little longer than last time was because we added this monstrosity at the end, which not only creates a mesh but also colors that mesh, and I mean it's you see, this Delaunay mesh itself takes about 1.1 seconds to calculate. So yeah, so we have this, and I mean, this was just one way to use it. You could do, you know, 100 other things with this Mandelbrot set. So with that, I hope you learned something from this video. Something. But yeah, if you didn't, then feel free to say something mean in the comments. But if you did learn something, then please do like and share and subscribe and all that nonsense that every YouTuber says. Thank you very much, and bye-bye.